Hello students, welcome to EPG Pathshala. I am Dr. Devvrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Magnetic Properties 2 from paper Electronic, Magnetic and Optical Properties of Materials. From this module, students may get to know about the magnetostatic energy, reciprocity theorem and their derivation, calculation of dipole-dipole interaction energy in a solid, and expression for the energy associated with a static magnetic field is also done. Magnetostatic energy. There are two main contributions to the energy of a ferromagnetic body: atomic scale electrostatic effects like exchange or single ion anisotropy, and magnetostatic effects. The magnetostatic effects, which involve the self energy of interaction of the body with the field it creates by itself, as well as the interaction of the body with the steady or slowly varying external magnetic fields, are considered here. The magnetostatic interactions are rather weak compared to the short-range exchange forces responsible for ferromagnetism, but they are important in ferromagnets nonetheless because the domain structure and magnetization process depends on them. It is the long-range nature of the dipole-dipole interaction varying as 1 by r cube that allows these weak interactions to determine the magnetic microstructure. The magnetization of a typical ferromagnetic is of the order of 1 into 10 to the power 6 ampere per meter, and the demagnetizing fields HD, though smaller, are similar in magnitude. Magnetostatic energies minus half mu 0 HD dot m are therefore of the order of 10 to the power 6 joule per meter cube. An atomic volume is typically 0.2 nanometer whole cube, so the corresponding energy per atom is 1 into 10 to the power minus 23 joule, is equivalent to a temperature of about 1 Kelvin. Generally, any product of a quantity with the dimension of B with a quantity with the dimension of h, B dot h, B dot m, mu 0 h square, mu 0 m square, such as has dimensions of energy per unit volume. Magnetic fields do no work on electric currents or moving charges because the magnetic part of the Lorentz force J cross B per unit volume or V cross B per unit charge is always perpendicular to the motion. We cannot associate a potential energy function with the magnetic force. It is necessary to consider the work done by the transient electric fields when establishing a particular magnetic configuration MR, or in setting of a particular current distribution GCR, in order to calculate the associated energy. Magnetostatic energy calculations can be rather subtle, and it is necessary to be clear about which energies are taken into account. For example, when a spanner is attracted towards an electromagnet, the energy of the spanner is lowered, but there are also modifications of the field both inside and outside the magnet, as well as the appearance of a demagnetizing field in the spanner. The energies associated with all these changes cancel out. Forces are nonetheless exerted and the damage may be done. Let us first consider a small rigid magnetic dipole M in a pre-existing steady field B. We omit a prime because the dipole has no internal structure. The moment experiences a torque tau, which is a function of n and m, tau into nm is equal to m cross b. Taking the reference state at theta is equal to 0, where theta is the angle between m and b, and integrating the torque gives the potential energy epsilon m is equal to integration over 0 to theta tau d theta prime, which depends on the angle. Apart from a constant, epsilon m is equal to minus m dot b. We assume that turning the magnetic dipole has no effect either on its moment or on the sources of B. Equation 2 is the Zeeman energy of the magnetic moment in the external field. Although there is a torque there is no net force on a magnetic moment in a uniform field. The potential energy does not depend on position. However, if V is non-uniform, the energy of the dipole does depend on its position. The net force Fm is equal to minus of grad of epsilon m, resulting from 2 is Fm is equal to grad of m dot V. The energy epsilon m is minimized for a ferromagnet or paramagnet by this force tending to pull the material into a region where the field is greatest, but a diamagnet is pushed out to a region where the field is smallest. Next, we consider the mutual interaction of two parallel dipoles M1 at R1 and M2 at R2. The interaction between the pair epsilon p may be considered as the energy of M1 in the field B21 created by M2 at R1 or vice versa. Epsilon p is equal to minus M1 B21 is equal to minus M2 B12. Hence, epsilon p is equal to minus half into M1 dot B21 plus M2 dot B12. The interaction of the parallel pair is anisotropic. From equation, the field of a dipole in polar coordinates Br is equal to 2 into mu 0 m by 4 pi r cube cos theta and B theta is equal to mu 0 m by 4 pi r cube into sin theta, V phi is equal to 0. And equation 2 gives epsilon p is equal to minus of 2 mu 0 m square by 4 pi r cube in the nose to tail configuration, whereas epsilon p is equal to mu 0 m square by 4 pi r cube in the broadside configuration. Hence, we have taken m1 is equal to m2 and set is equal to modulus of r1 minus r2. Hence, freely suspended dipoles tend to aggregate in threads. Figure 1 shows the nose to tail and broadside configurations for a pair of magnetic dipoles. In A is lower in energy and for B it is unstable. Reciprocity. The two dipoles are an example of the reciprocity theorem, a useful result in magnetostatics, which states that the energy of interaction of two separate distributions of magnetization M1 and M2 producing fields H1 and H2 is epsilon is equal to minus of mu 0 into integration over M1 dot H2 d cube r, which is equal to minus of mu 0 into integration over M2 dot H1 d cube r, where epsilon is the interaction energy. The reciprocity theorem is used to simplify magnetic energy calculations, such as the interaction of a magnetic medium with a reed head. For example, H local is equal to Hd plus Hl. Self-energy. These ideas can be extended to calculate the dipole-dipole interaction energy in a solid. We consider the energy of a body with magnetization MR in a magnetic field. The result is different according to whether the field in question is an external field H or the demagnetizing field Hd created by the body itself. Here we discuss the second case, considering first a small moment delta m at a point inside the macroscopic magnetized body. The energy needed to bring the small moment into position is delta E is equal to minus mu 0 delta m into H local, where HL is Lorentz cavity field and is given by HL is equal to m by 3 and delta epsilon is equal to minus of mu 0 delta m into Hd plus Hl. Integration over the whole sample gives epsilon is equal to minus half into integration over mu 0 Hd into m into d cube r minus 1 by 6 of integration over v into mu 0 m square d cube r. The factor of half, which always appears in expressions for the self energy, is needed to avoid double counting because each element delta m contributes as a field source and as a moment. This energy is plotted in figure 3 for a uniformly magnetized ellipsoid of revolution. for which epsilon is equal to half into mu 0 v into n minus 1 by 3 into m square. The second term is actually unimportant. It tends to align the moments all in the same direction, but it is much smaller than the exchange energy, which has the same effect. The magnetostatic self-energy is conventionally defined as epsilon m is equal to epsilon plus 1 by epsilon integration over, which is a multiplication of mu 0 m square d cube r, so that epsilon m is equal to minus half into integration over volume of mu 0 hd into m into d cube r. Since m is equal to b by mu 0 minus h, the integral may be written in the equivalent form epsilon m is equal to half of integration over mu 0 hd square into d cube r, where the integral is now over all space. We have used the handy result that for a magnet in its own field when no currents are present is equal to b dot hd into d cube r, which is equal to 0, where the integral is again over all space. Figure 3 represents the dipolar self-energy for an ellipsoid of revolution. This shows that the energy associated with a permanent magnet can be either associated with the integral of hd square over all space or with the integral of minus hd into m over the magnet, but not both. These are alternative ways of regarding the same energy term. In the special case of a uniformly magnetized ellipsoid gives epsilon m is equal to half of mu 0 v into n into m square, which is the same as the energy plotted in figure 3. Apart from the constant term, the expression 8 assumes the magnetization is known in advance, so we can evaluate the magnetostatic energy in the field produced by the magnetization configuration. In practice, the magnetization tends to adopt a configuration which minimizes its self-energy. For an ellipsoid, there may be uniform magnetization along the axis where n is smallest. Energy associated with a magnetic field. An expression for the energy associated with a static magnetic field may be obtained by considering an inductor L consisting of a current loop which creates a flux phi is equal to L into I by Faraday's law. Epsilon is equal to minus d phi by dt, where epsilon is the electromotive force. EMF developed in a circuit and phi is the flux threading it. So, the power needed to maintain a current I in the inductor is epsilon into I is equal to Li into di by dt. Integrating from 0 to I gives an expression for the energy associated with the inductor. Epsilon is equal to half Li square, which is equal to half phi into I. The same energy can be associated with the field in space created by the current in the inductor. First, the flux is expressed in terms of the vector potential A using Stokes theorem. Integration surface integral over B dot dA is equal to closed loop of A dot dl, and the energy is written as epsilon is equal to half of closed loop integration over I into A into dl. This can be generalized from a single current loop to a continuous current density by replacing L IDL by J d cube r. Hence d cube r is equal to d square r into dl, which is equal to dA into dl, and J is parallel to the area vector A parallel to dl, and therefore J into d square r into A dot dl is equal to J dot A into d cube r, where JdA is the current di in a tube of cross section dA. The general expression for the energy associated with a magnetic field distribution is therefore epsilon is equal to half of integration over J dot A into d cube r. This is analogous to the expression for the electrostatic energy, which is equal to epsilon is equal to half of integration over rho into phi epsilon d cube r. Finally, equation 11 is expressed in terms of the magnetic field. Since F is equal to or J is equal to curl of H, and curl of H dot A is equal to grad dot H cross A plus H dot curl A, there are two terms in the integral. The first is 0 for a localized field source, since by the divergence theorem the integral is equal to the flux of h cross A through a surface at infinity. Hence, the only remaining term is epsilon, which is equal to half of integration over h dot b dq bar. In the free space, this becomes epsilon is equal to half of integration over mu 0 h square into dq bar. The total energy density associated with the magnetic field is half mu 0 h square. This is actually a general statement irrespective of whether the field is created by electric currents or magnetic material. When designing magnetic circuits that include permanent magnets, the aim is usually to maximize the energy associated with the field created by the magnet in the space around it. From equation 8 and 9, we have half of integration over mu 0 hd square into d cube r is equal to minus half into integration over v mu 0 hd dot m into d cube r, which may be rewritten as half of integration over mu 0 hd square d cube r is equal to minus half of mu 0 hd square d cube r minus half of mu 0 hd dot m into d cube r, where the indices O and I indicate integrals over space outside and inside the magnet. The integral on the left is the one to be maximized. For a uniformly magnetized ellipsoid, the sum of the two integrals on the right over the volume of the magnet is half of minus half mu 0 m square. This is maximum when the demagnetizing factor n equals to half. The ideal shape for a permanent magnet is therefore an ellipsoid of revolution with c by a is equal to 0.5. A cylinder with height equal to radius is almost as good. The energy stored in the field outside the magnet on the left side of 14 is equal to minus half into mu 0 hd square dq bar. The integral minus half integration over mu 0 hd dot b into dq bar is known as the energy product. It is twice the energy stored in the stray field of the magnet. Again, the usable energy may be associated either with the stray field half into integration of mu 0 hd square dq bar or with the demagnetizing field in the magnet itself, which is equal to half of integration over mu 0 hd dot m into dq bar, but not both. The two terms have the same absolute values, but their sum is 0. It is a matter of taste. Energy in an external field. To extend the energy expression of a point dipole in an external field to ferromagnetic materials, it is not adequate simply to fill the inductor with a medium of permeability mu, because ferromagnets are generally nonlinear. B is not equal to mu 0 h. They exhibit hysteresis, so that the energy needed to prepare a state described by B and H depends on the path followed. We can, however, evaluate the increment of work delta W done to produce a small change in the flux delta phi. So delta W is equal to minus epsilon I delta T, which is equal to I into delta phi. But by Ampere's law, I is equal to integration over h dot dl, where the integral is taken around a closed loop. Hence, delta W is equal to integration of in a closed loop of h dot delta B into dq bar, where the integral is over all space. When the magnetization is uniform, this expression becomes delta W is equal to h dot delta B, where delta W is the energy increment per unit volume. More generally, we would love to have an expression for the energy of the magnetization distribution MR in the external applied field H, which is supposedly only found by the presence of the magnetic material. It is rather unrealistic even for good permanent magnets to assume a perfectly uniform magnetization. MR is modified by the field applied during the magnetization process, and it depends on the value of HR throughout the body. We do not know that what HR really looks like inside the magnet. It is not obvious that it is possible to find such an energy expression in terms of H prime. The real H field which is present throughout the material and the one which features in Maxwell's equation is H is equal to H prime plus HD. where Hd is the demagnetizing field produced by the material itself. The basic constitutive relation for the material is m is equal to mh, not m is equal to mh prime, precisely because we did not want it to depend on extraneous features like sample shape. The applied field H prime is supposed to be created by some external current distribution J prime. It satisfies curl H prime is equal to J prime and divergence of H is equal to 0. When there are no currents in the region of interest, the mesoscopic magnetostatic field Hd created by this satisfies divergence of Hd is equal to minus of divergence of M and curl of Hd is equal to 0. The corresponding induction is B is equal to mu 0 H plus M, which is equal to mu 0 into H prime plus Hd plus M. The general expression for the magnetic work done in changing the induction by delta B is given by the equation 15 with H is equal to H prime plus Hd. This expression includes a term associated with the H field in the empty state. Integration over mu 0 H prime delta H prime d cube r, which is unrelated to the magnetic body and should be subtracted to leave an expression for the work associated with the energy changes of the magnetized body alone. The relevant magnetic work is therefore delta W prime is equal to integration over H into delta B minus mu 0 H prime dot delta H prime into d cube r. Using the expressions for H and B, H dot delta B is equal to mu 0 into H prime plus Hd into delta H prime plus delta Hd plus delta M. Hence, delta W prime is equal to mu 0 into integration over delta H prime dot Hd into d cube r plus integration over Hd into delta Hd d cube r plus integration over H dot delta M into d cube r. The first integral is 0 for the same reason that B dot Hd into d cube r is 0 over all space, divergence of H prime is equal to 0 and curl of Hd is equal to 0. The second integral is the contribution to the magnetostatic self energy. 9. Delta W prime is equal to delta of epsilon m plus mu 0 into integration over B H dot delta M into d cube r, where the integral is over the volume of the magnet as m is equal to 0. Elsewhere, this expression relates the magnetic energy to the self energy, and the constitutive relation m is equal to mh from equation 8 is equal to delta epsilon m, which is equal to minus half of mu 0 into integration of V Hd delta m plus m dot delta Hd into d cube r. Delta epsilon m is equal to minus of mu 0 into integration of V H dot delta m into d cube r. By reciprocity, by H is equal to H prime plus Ht, delta W prime is equal to mu 0 into integration over H prime dot delta m into d cube r. Equation delta W prime is equal to mu 0 into integration over H prime dot delta m into d cube r is the expression we sought for work done on the body by the applied field. The integral is over the body, even though is not the field appearing in the constitutive relations. The work is expressed in terms of the quantities of direct physical interest, the applied field H and the magnetization M. The expression reduces to delta W dash is equal to mu 0 H prime dot delta M, where delta W is the energy increment per unit volume. If we consider a magnetic material with B and M curves as shown in figure 4, the integrals are as indicated in the figure caption. The energy integration over 0 to M mu 0 H prime dot dm expended to magnetize a sample is related to its anisotropy energy, including shape anisotropy, since the magnetization process in the external field depends on the orientation of the sample. If the mh prime relation is hysteresis, energy is expended on the cycling the field H prime. For example, figure 4b shows the energy expended to magnetize the sample to remanence. Figure 4 shows the energy associated with the magnetization curve. The shaded area in A indicates that the energy associated with the applied field, whereas that in B represents the work done to magnetize the material, and that in C represents the hysteresis loss per cycle, and figure 4C shows the hysteresis loop on a complete cycle of mu 0 h prime dot dm. An expression for the energy needed to magnetize a LIH permanent paramagnetic material in an external field may be deduced from equation 23. It gives W is equal to integration over 0 to m mu 0 h prime dm prime is equal to half of mu 0 m h prime. So students, let us summarize what we have learnt in this module. Brief discussion on magnetostatic energy and its derivation, reciprocity theorem and its derivation, dipole-dipole interaction energy in a solid is calculated. An expression for the energy associated with the static magnetic field is also obtained. Thank you.